public key infrastructure, PKI. Some people get really anxious when they hear this definition. They think, is it some kind of a law? Is it like GDPR? Or is it something related to roads, public key infrastructure? Is it something related to keys? And when people see it in the context of cybersecurity, this gets even more confusing. They can't understand, like, how did we go from cryptography, from algorithms, from asymmetric keys to public key infrastructure? Well, in this video, we'll be discussing this topic in more depth because it's one of the key pillars of cybersecurity, at least in software industry. And that's why we need to know more about it. And obviously, we will discuss why it's called that way. To start with, in order to be able to unite this definition with more common definitions that are used in the industry, remember that public key infrastructure is about asymmetric cryptography, asymmetric encryption. We have discussed it in more detail in my previous video about cryptography with more general foundation about the topic. Asymmetric means we use different keys, we use different devices, different means in order to decrypt a message, decrypt a file. Generally speaking, we have a public device, public key that is commonly called, and private key. So these two sets of keys are used in this kind of encryption. We have a diagram that we will look into shortly in order to understand how these two keys are used together. That's why it's called asymmetric. So whenever you hear asymmetric cryptography, asymmetric encryption, or PKI, remember that it usually refers to the same definition, to the same infrastructure. And it's called infrastructure because it has become so popular. This type of encryption is being used in HTTPS, right? The protocol we use on a daily basis when we access applications in our browsers, when we access applications on our mobile. We use HTTPS all the time. Then in PGP, pretty good privacy. This is one of the email protocols that is considered one of the superior protocols because of its privacy offering and its encryption offering within the protocol. And of course, SSL and also TLS. SSL has been deprecated, so TLS would be better in this scenario. In TLS encryption, I have a video about TLS encryption where we discuss it in detail, how public key infrastructure is used in TLS handshake within HTTPS. So it's a very common, very omnipresent definition. That's why it's being called infrastructure at the moment, because almost every application needs a set of keys. Almost every browser, every user needs a set of keys in order to be within that encryption cycle, encryption handshake, to put it that way. That's why it's called public key infrastructure. Obviously, we rely on key generation in public key infrastructure. We rely on different type of algorithms. One of the most common algorithms that encrypts data in chunks, 128, 192, and etc., and does several sets of encryptions. So, for example, it has an algorithm to follow to encrypt something on a very basic level. We move alphabetical numbers or numerical digits by one to the right? And they do these encryption cycles many times on the same data chunks after dividing the data. So we focus, key generation happens with help of algorithms or RSA. RSA, it relies on big prime numbers, and these prime numbers are being multiplied in order to generate the final string, encrypted string. Again, you can do your own research in order to go into more depth on the algorithms, because they are obviously a very big topic, given that they're being used all over the world. And another one is ECC. We have elliptic curve cryptography. We have talked about it too in my previous video about cryptography. These three algorithms are most common ones. And key generation happens with the help of algorithm. However, private and public key are mathematically connected, right? Because the string, the character, the message, the file, whatever you would like to encrypt, is encrypted with public key. And the same encrypted message can be decrypted only with private key. That's why these keys are mathematically connected to ensure that something that has been encrypted by one key can be decrypted by another key. However, there is one more definition. And you must have heard it, even if you have been working not in IT industry, because when I started my career, I was working in project management. It wasn't quite IT industry. And even back then, I heard the definition of digital signatures quite often. And encryption and digital signatures is not the same definition exactly, because we will look at it in the diagram shortly. Now we're just discussing, I'm giving you some theoretical foundation because before we go into more definitive flows. In encryption, you encrypt the message and then receiver receives it and decrypts the message. This is the encryption. Very, very simple in a very, very basic definitions. In digital signatures, we do validation. We don't do encryption. Validation. You might think, are these mutually exhaustive? No. Usually encryption is used with digital signatures, especially in email communication, right? Because whenever we receive an email signed with digital signature, it's usually hash function. We calculate hash function for that email to see if it's the same hash function that we have calculated. If it's the same, it means that we validated the email. This email really comes from the sender from whom we think it came from. And even in this example, we still need two pairs of keys, because we can use public key to generate a hash along with encryption, and then private key of the receiver can be used in order to generate a hash of the message before decrypting it, in order to verify, validate. Is it the message? Is it the message that's from sender I'm expecting it from? That's the difference. So encryption is where you encrypt, decrypt, but digital signatures offer validation, authentication. It's similar to the passport. Whenever I travel abroad, I have my passport in order to validate my identity, because without the passport, I can claim whatever I want. I can claim that I'm a citizen of Maldives if it comes to it. But that's not the case, right? I might have a different passport, I might have a different name and surname in the passport. So that's my verification, and my biometrics, my fingerprints are my verifications. So that's why we need digital signatures. We have covered that public key infrastructure is widely used in most common protocols that we use on a daily basis, even if we don't realize. I have videos, by the way, on TLS handshake. I have videos on HTTPS. Please don't forget to check it out on my channel. So it's very, very omnipresent, and it's multi-billion-dollar industry. Security, it's a multi-billion-dollar industry. Even those one-time codes with numbers that you receive is a multi-billion-dollar industry, and public key infrastructure as well. But this helps us to be secure in the world of World Web. And since we need some verification that for public keys, private keys, how do I know whose public key pair it is? How do I know whose digital signature it is? We don't know. That's why we needed some public bodies, some companies, to put it that way, that would provide us a verification, that would provide us with their reputation, that would assure us that this is the public and private key of that application. And these authorities, called certificate authorities, you usually wouldn't see it as certificate authorities. Most commonly, they are referred as CAs, as I wrote here. This is the abbreviation. So whenever you see CA, this is certificate authority. So what do these authorities do? These authorities, they provide certificates, public and private keys, from applications, from browser, for applications mostly, in order to verify, and they do verify, that this is the public and private key of that application. Because during TLS handshake, or during establishing the verification, we go and we see there is a public key of the application. But how do we know if it's the public key? Let's see who issued that public key. Okay, this was issued by John Doe's certificate authority. Don't mind me, certificate authorities shouldn't be named after people. It's just an example. And I go back to the certificate authority and I say, certificate authority, was it you who issued that public key? and certificate authority turns back and says, yeah, it's me, I recognize that public key, you have my signature or stamp of approval. And that's how we know that this public key was issued by that specific certificate authority. Obviously, the certificate authority topic deserves another video of its own, and we will discuss it further in my next video. But you need to know at least some introductory information about it, and it's a very, very important topic on itself. Think of it as a passport office. Every country has its own passport office, right? Let's say UK, the United Kingdom. It has its passport office and it issues passports. In the passports, it has some certain definitive characteristics. Passports usually have a microchip in order to prove that this passport has been issued by the passport office of the United Kingdom. And it holds true for every country. They usually have their microchips in the passports, and that's why this passport, people like they do slide our passport and see who it is. This is similar, so they help us to verify if the keys that we have, if the information that we have is authentic. Because I can log in into my computer and try to generate a key, right? How do you know if it's a public key of google.com or public key of jamaabouttech.com? You don't know. That's why you need a verification from certificate authority. Before we proceed to the diagrams, I think it's important to mention the main limitations of public key infrastructures that we have at the moment. One of the limitations, there are two main limitations, right? On top of others, more minor. First is quantum attacks. So with the algorithms that we have at the moment, with classic computers compute power, it's very difficult to crack that algorithm and go to the decrypt the algorithm. When we see different news articles that this university has the biggest computer now, or this government has the biggest computer now, some people might think, okay, they have the biggest computer now, but what's the point? I can buy an expensive laptop and it will be fast, it will be cool, and I can use it. Well, the point of that is that the bigger the computer is, that's a rule of thumb, usually, not necessarily, but usually that's the case. The more compute power it has, the more built-in memory it might have. That's why it might be easier for the bigger computer, for a better computing power, to decrypt algorithms. Even if in RSA algorithm we find two large prime numbers, we multiply them, we do several units of multiplication in order to get the encrypted value, computers with better power can achieve it very fast. And quantum computing refers to computing power that is better, that is superior to classic computers. That's why quantum attacks are a real thing in public key infrastructure. And that's why at the moment many professional mathematicians are thinking about pro-quantum algorithms in order to come up with new algorithms that can stand up to those quantum attacks. If you ask me, I don't think that we will be too vulnerable to quantum attacks, because as long as there are mathematicians who think about pro-quantum algorithms in order to develop new algorithms, we will still be okay in light of better computing, in light of better AI, and etc. However, even if not quantum attacks, every organized crime, cybersecurity crime organization, tries to, that's its job, it tries to crack the encryption, right? So after a certain point in time, every government or these groups of mathematicians, they try to create new algorithms, new protocols. That's why it's an ongoing process. Before we came to AES, RSA, ECC, there were many other algorithms that have been obviously used at some point, but then discouraged from use because they were cracked. The second disadvantage of asymmetric cryptography or public infrastructure is compute power. Right? Remember that you need to generate two keys, one public, one private, and you need more compute power for that. That's why if you watch my video about TLS handshake, you will see that the handshake starts with asymmetric cryptography. And once the handshake has been established, they switch to symmetric cryptography in that connection after establishing handshake. Why? Because it would be very expensive to keep that connection on asymmetric key cryptography and generate two keys all the time. It requires more compute power, and in the end it increases the latency, the time by which you receive the assets, the data from the website. That's why compute power is one of the disadvantages, but yet because asymmetric key cryptography offers better security than symmetric key cryptography, we're still sticking with symmetric key cryptography and thinking about ways around it. And TLS handshake is one of the good examples where you start with asymmetric and then you continue with symmetric key cryptography. Now, when you have a foundation, how it works, why we have it, what its disadvantages are, and you know more or less about its key algorithms, let's look at the flow, how public and private key cryptography works. Because before you see the flow, it might still be not that clear for you. Well, usually on the internet, in diagrams, they use Bob and Alice in all examples. I think I also used those names in my TLS handshake video. So I decided not to be discriminatory and use other names for once. That's why today we're looking at a conversation between Ali and Paul. If you know which series Ali and Paul are from, please comment them down below under my video if you watched them or if they're familiar to you. Anyway, let's start. So we see the conversation between two people, and Paul writes a message to Ali, right? It can be in WhatsApp, it can be in Telegram, it can be an email. For the purpose of this example, the platform doesn't matter. But the platform is using the asymmetric cryptography or public key infrastructure. And Paul says, "Hi, Ali," right? Paul has Ali's public key because they are in conversation with each other. Paul uses Ali's public key, Ali, right, in order to encrypt that message. After encryption, we get some gibberish text. We don't necessarily get what I wrote here, but whatever you get is gibberish and you can't understand anything. But that's the encrypted message. Then Paul sends the message after it has been encrypted. And while in transit, the message goes through the transit in an encrypted form, right? And then Ali receives the message. At this point, Ali received it, and Ali has her own private key because that's her key, and she doesn't have to use her public key. Her public key will not decrypt the message. It's only one key that can decrypt it, her private key, apologies. Now she uses her private key to decrypt the message. You see, both keys are Alice, right? Public key is Alice's key that is available for distribution. She sent it to Paul. And private key is not available for distribution. She should keep it with herself, and that's Alice's key. She decrypts the message, right, with her private key, and she gets "Hi, Ali," the message that she intends to receive from Paul. What would happen if she couldn't decrypt this message with her private key? Well, it would mean that the message has been tampered in transit. Some bad actor tampered the message. Then when she tries to decrypt the message encrypted with her public key, she can't, because she can see that the message has been tampered with. And that's an important point to remember. So this is the flow of how we use private and public key infrastructure. On this flow, I would like to integrate digital signature in order to show how digital signature is being used with public key infrastructure with encryption, because in fact it's very common for public encryption and digital signatures to be used together, right? So imagine we are now sending this message on a platform that is using digital signatures. Let's suppose that it's an email, a Gmail, right? And now Ali decides to reply to Paul over an email, and she says, "Hi, Paul." Then she uses Paul's public key. This public key is Paul's. She uses Paul's public key to encrypt the message. She encrypts her message with Paul's public key, and we get some gibberish message again because it's encrypted. We're not supposed to understand it. And once it's encrypted, she generates a hash of her message. That's where we digitally sign, it's also called, like referred to. We generate the hash of the message that is being sent along with the email. Once the hash has been generated and the message was sent to Paul first verifies the hash. He verifies that, okay, this is the same hash, so this is the same message that comes from Ali. Then he uses his private key to decrypt the message and see the message in plain text. There are some different mechanisms that are being used. Under different mechanisms, I mean hashing can occur at different stages. So we can do hashing before encrypting the plain text message, so we can generate the hash of hi Paul, or we can generate the hash of encrypted message, right? The hashes will be different because obviously these are different messages in its unencrypted and encrypted forms. However, the hashing can move to a different point. But the whole point of digital signature is to verify whether the message is coming from Ali. This is a second step on top of encryption, which makes it harder for a bad actor to intercept, to tamper with the messages. That's how these two, encryption and digital signatures, work together. So that's it for this lecture. If you have any questions, please leave them in the comment section down below. Don't forget to subscribe to my channel because YouTube has its own algorithms. Although they might not be the cryptography algorithms, AES or RSA, but yet it does have its own algorithms for that, if that matters. So please don't forget to subscribe to my channel and to like to my video so that this mysterious algorithm likes my channel and promotes it more. Thank you for being with me today and see you in the next video. Bye!